time to get started, and I thought I'd just try to recap what we did last time in summary form. So we talked about how we're going to describe pairs of particles, multiple particles. And you might think, well, we did this with the hydrogen atom, but we didn't really describe the proton. We were assuming the proton was sort of fixed, and it was just there to generate the force that the electron was feeling. But now we're going to legitimately allow two particles to be sort of moving around, and there's going to be a wave function associated with the two particle state. And the way we decided we were going to do that was to, instead of just having a psi as a function, at some particular time, here I'm saying t equals 0 to describe the state it's in, we're going to have a function where I'm imagining here that these particles live in one dimension. X1 is sort of the coordinate of particle 1, X2 is the coordinate of particle 2, at least classically, that's how we'd think about it. And we specify some function of X1 and X2, or if we're in 3 dimensions, we need 6 variables there, X1, Y1, Z1, X2, Y2, Z2. And the probability density, well, so I could sketch what this function is in the X1, X2 plane. It's a function of 2 variables. And we did a little bit of that on the first worksheet that we were working on last time. To get the probability density, which is also a function of X1 and X2, and we could also sketch in this plane, of course, we just take the magnitude squared of this function. And that was the point where we discovered that if there are such a thing as identical particles, if there's no way in principle to distinguish between one electron and another electron, or one proton and another proton, then, if you can really have any shape you want in this plane for the probability density, then it's saying that the probability of measuring particle 1 in a certain region is different than the probability of measuring particle 2 as a function of position. And that's inconsistent with, or at least it doesn't seems to be too much information if we really can't tell apart X1 and X2. In other words, if I measure X2 or particle 2 in a certain location and particle 1 in a certain location, I don't know which one I've measured in which location if they're truly identical. So the way we were going to fix that is to add something into our theory and demand that these states, and again here, because we're lazy, we don't want to write X1 and X2, I'm just writing 1 and 2. Those stand for X1 and X2. We're going to demand that our states are not just any old function of X1 and X2, but they have to be eigenfunctions of the exchange operator. And the function of the exchange operator is just to switch the variable X1 and X2. So P acting on psi of X1 and X2 gives psi of X2 and X1. And we're going to demand that when we apply the exchange operator, the state is not changed in any important way. When we apply the exchange operator, we get a multiple of the same state back, and that means that the probability densities won't change when we exchange the 2 particle coordinates, and therefore we're going to get probability densities that are symmetric in X1 and X2 in a certain way. Okay, and then we did a little proof that, very easy proof, that this eigenvalue had to be plus or minus 1, because when we apply the exchange operator twice, it just gives the same function back. So lambda had to be plus or minus 1. And the last thing I think we discussed right before the end of the period was that, there was some reference to a theorem that Griffiths proved back in the energy-time uncertainty relation, where states that have definite exchange eigenvalue, in other words, they have a definite eigenvalue at time t equals 0, remain definite exchange states. In other words, they remain eigenfunctions of the exchange operator for all time with the same eigenvalue. So once you start out in a +1 state, you stay in that +1 state. And so if we have identical particles, so we take electrons. there's going to be some certain eigenvalue associated with electrons, either +1 or -1. It's going to stick for the rest of time. And so we're just going to think of that as an immutable property of electrons. They have a certain eigenvalue of the exchange operator that's relevant when we have multiple electrons around. Protons, same way, and other elementary particles, same way. And the last definition we covered last time was that particles that are symmetric under exchange, in other words, their exchange operator eigenvalue is +1, are called bosons. And those that are anti-symmetric under exchange, they get the -1 sign, are called fermions. Okay, and that's because that property is sort of immutable. If a pair of electrons has that property, either the +1 or the -1 at time t equals 0, then they have that property for the rest of the time. We may as well just think of that as a property of electrons themselves. You've learned, I'm assuming in modern physics, that there's a relationship between the spins of particles and whether they're bosons and fermions. So sometimes people call that the spin statistics connection, because this affects, kind of how, we won't talk about it much in here, but there's a lot of connections with statistics of measuring these particles. So this statistics refers to this boson fermion property, and the spin refers to their spin value. And in non-relativistic quantum mechanics, this is just an amazing coincidence that seems to be experimentally observed. Particles that have integer spins are always bosons. And particles that have half-odd integer spins, that means like your protons, neutrons, and electrons, are always fermions. Okay, integer spin particles would be like, well, we don't have photons, but pions have integer spins, and so they would be examples of bosons. Yeah, I've never seen the proof, but people tell me you can prove this in quantum field theory. Okay, that's a step up from our non-relativistic quantum mechanics, that you can prove that there has to be this connection between bosons and fermions and the spins of the particles. I have no idea how that goes. So we're working our way through a worksheet. I guess I better give this to Jake. We're supposed to do problem number 3 on there, which asks about identical fermions. This is the worksheet we're working on Monday, and it's listed under Monday's date if you don't have a copy with you and you're on Zoom. And I better go print myself out another copy since I just gave away my last copy. But work on that problem for a minute. Okay, let's talk about the answers here, at least to A and B, but I think we may as well do the rest together. Is the two particle state given in problem 1? That's what I've written up here at the top. The product of the Gaussian in the variable x1 and the Gaussian in the variable x2. This is supposed to be a 2, not a 1 there. And those Gaussians are centered at different x's. One's centered at x equals 2 and the other one at x equals minus 2. Is it an eigenfunction of the exchange operator? In other words, is it going to be an allowed wave function or state for a pair of identical particles without specifying what kind of particles it is? No, it's not, because it doesn't give a multiple of the same state back when I exchange x1 and x2. One way, just to use the work down here, when I exchange x1 and x2, this kind of piece changes into this kind of piece, which is a fundamentally different function of x1 and x2. It's going to have a different graph in the x1, x2 plane, so it's a different function. How about if I apply it to the state that was given in problem 2, which is written down below here? Yeah, when I exchange x1 and x2, this term turns into this term, and this term turns into this term, and so I get exactly the same state back, and that means it's an eigenfunction of the exchange operator with eigenvalue +1. And now so the answer is B, yes, and the eigenvalue is +1. In C, we see that, again, this is not an allowed, we already know it's not an allowed state for any kind of identical particle. This one apparently is associated with bosons. It would be an allowable state that a pair of identical bosons could be in because it's got an eigenvalue under exchange of +1. What about if we have a pair of identical fermions? How would we sort of create a state that's as much like this one as possible, but appropriately having the appropriate property under the exchange operator? What do we do? In other words, if it's for fermions, I better get a minus sign when I apply exchange. How do I need to, we got a plus sign here. How do I need to change this function? Yeah, switch the plus to a minus sign in the middle. So the answer in part C of this is that, so this, or I guess it's problem 3C. I'm just going to amend my work here because I don't want to rewrite the whole thing. The only difference is I need a minus sign there. And that process of going from a non-allowed identical particle state to an allowed identical particle state under our new postulate about the exchange operator is called either symmetrizing the state, that's what we did to go from 1 to 2, or anti-symmetrizing the state, that's what we did to go from the function in 1 to the one that's asked for in 3C. So we've anti-symmetrized this state. This state anti-symmetrized gives this, which all that means is switch the variables and put a minus sign in front of it and add those two together. Okay. Sketch the probability density for the anti-symmetrized state. This is D in the x1, x2 plane. Okay. Now, before, it's been a while since Monday when we sketched these. We didn't have to worry about minus signs. Everything was positive, right? Because we, at least if we had the plus sign there, this function never went negative if this is positive. This one never goes negative, so we didn't have to worry about negatives. Here, this function, because of the minus sign, is actually negative in some regions and positive in other regions, right? So I would say it seems like this term is going to be maximal when x1 is near 2 and when x2 is near minus 2. x1 is near 2 and x2 is near minus 2. That's in this region down here. And that means if I were to draw some level curves, I would say these are negative level curves. And this is the maximum negative value. So we're at the bottom of kind of a valley there if I were drawing a surface that describes the function. I'm sorry, that one's positive. I got it wrong. I was thinking ahead to the other one. This is the one that's got the negative, right? So this is saying when x1 is near -2 and x2 is near +2, we get something that has negative values. And it's maximum negative when these things are the maximum size. And this product of function is actually really small there, so it doesn't add much onto it. So these are negative level curves. This is a maximum negative value, which means it's the bottom of a valley. Okay, so that would be a picture of what psi itself looks like. And I think we're not asked for that here. We're actually asked for what rho looks like. Rho is the magnitude squared of that. So if I wanted to change this to a picture of rho as a function of x1 and x2 for this identical fermion state, you know, am I drawing sloppy enough? It's just all the negative stuff gets turned to positive. It changes the details of the function a little bit, but the basic shape, locations of the peaks are pretty much the same when we take the magnitude squared of it. Okay, and then let's see what's in E. I didn't have a chance to remind myself of that. For identical fermions confined to the x-axis, what's the probability of finding both particles in the same position? Well, let's see. If I measure the position, right, of the particles, you know, I might get a positive value for x1 and a positive value for x2, or maybe a positive value for x1 and a negative value for x2. If we're talking about the probability of getting the same values for x1 and x2, that's finding the particles in the same position. And here we're talking about fermions. That would be a point where x1 equals x2. So it would be like here, or here, or here. It would be on the line x1 equals x2. So we're asking, what is the value of the probability density along that dashed line that I've drawn there? And the answer is 0, because, well, before I squared it and got the probability density, this was negative here in an exactly symmetric way to how it's positive here, which means whatever it's doing over here, it's doing the negative of it over here. It's got to be passing through 0 along this line. And when I take the magnitude squared of that, it's still 0 at that point. So the probability density along that x1 equals x2 line is 0. Does your probability density reflect this? Does your formula in C reflect this? Yes. So the probability density reflects it. If I look at the formula we give in C, if I say I want to evaluate what the magnitude of psi is when x1 equals x2, well, when x1 equals x2, it doesn't matter which value I choose, right? So I say maybe x1 is 3 and x2 is 3. This term is exactly the same as this term there, and therefore they subtract off and give 0. So the value of psi is 0, and therefore the value of rho, which is the magnitude of psi squared, is 0. Okay, just trying to familiarize ourselves with these probability densities as a function of 2 variables. You know, I'm trying to do the simple case. In general, in 3 dimensions, we would have 6 variables. So it's kind of hard to wrap your head around it. But the same properties that happen when we just imagine these particles living in 1 dimension. So they're living on the x-axis. Both of them live on the same x-axis, I guess I should say, right? x1 just refers to kind of the closest classical concept to the position of particle 1 and the position of particle 2, but they're both on the same x-axis. They're both living in that 1-dimensional space. When we measure it, we might get particle 1 found here and particle 2 there, but they're on the same axis. Okay, let's go back to the slides. Any questions on that? Here's just some MATLAB pictures that I drew or that I produced to kind of show it in better, more exactly than I could do on the board. So if we draw it using the MATLAB surf function, here is the function that was given in problem 1. This is the one that's not an function of the exchange operator. And it's supposed to be that, it's hard to read the numbers here, but I'm drawing x1 along this direction, x2 along that direction. And we're seeing right here, x1 is 2 and x2 is -2 right there. That's where the peak of the given function was. And then it goes down from there. So those are kind of level curves associated with it. And then here's the corresponding function drawn in the three-dimensional sense, drawing height as the value of the function. It's turned around a little bit in that the origin's back here, x1's going along that direction, x2 is going along that direction. Then in problem 2, when we symmetrized, what that does is kind of take this function, flip it over the line x1 equals x2, so take that same peak and move it over here and add those two functions together. You still got to renormalize it. So this constant a that I had up here on the board, it's actually a different number, right? Because I've sort of changed the shape of the function. There's a different area under it. I would have to have a different normalization constant. Clearly, there's more area here, so I need to, a smaller normalization constant. And then the anti-symmetrized state, what I do is take the negative of the one with flipped variables, and that means I take this function, flip it over the line x1 equals x2, and then take the negative of it and add those two functions together. When you do, you get a function that's 0 right down the line that divides those, which is the x1 equals x2 line. Here you can see it more precisely. I didn't put a color bar on here, but this color, which is actually supposed to show up as green here, is is the height of the function at 0. That means the height is 0 right in there. And it's going positive over here in the red and negative over here in the blue, as kind of indicated by this projection down there. Okay, so those are the beginning of thinking about boson and fermion states, which are associated with bosons, integer spins, fermions, half-odd integer spins. All right, let's now talk about finding states of definite energy for multi-particle systems. And we're in particular going to concern ourselves with identical particles. But the first thing, this can be quite complicated, because, well, let me just follow the bullets I put down here. Of course, in chapter 4 and in chapter 2, even in one dimension, we were considering a single particle in a potential energy function, much like an electron subject to the potential energy of an electron-proton force in a hydrogen atom. And we were able to find definite energy states for the electron. We're now going to find states where we have two particles, a pair of particles subject to a potential energy function, such as we might have in a helium atom, right? We've got two electrons in a helium atom. They're attracted to the helium nucleus, which has positive, plus 2e charge on it. And we want to describe it, but there's a complication. The electrons, of course, are attracted to the helium nucleus, but they also repel each other because they're point particles with opposite signs, right? And so the potential energy function doesn't just include the electron nucleus interaction, but it also includes electron-electron interactions. And that, at least on paper, you can solve things like this numerically on computers, still not easy. But to try to get exact solutions doesn't work out nearly as nicely when you have the electrons interacting with each other. So we're going to do something that seems probably a little bit ridiculous, and it's amazing how much mileage you can get out of it. We're going to approximate this system of, say, a helium atom by imagining that the two particles we're describing actually don't interact with each other at all. So it's like having a helium atom where the electrons don't repel. They're still both attracted to the helium nucleus. They're still fermions, so they have to be in antisymmetric states. But we're just going to pretend that they don't exert any forces from each other. They only feel the forces from the external potential, which, in the helium example is the force on each from the nucleus, but they don't exert a force on each other. We call that non-interacting particles. Okay, seems kind of ridiculous, but for charged particles, they are going to interact strongly. But when you look at how much of an error you make in terms of the states comparing with the real solutions in measurements, you'll find out that it's not a terrible approximation. Okay, so let's first go back to forget about indistinguishable or identical particles. Let's talk about distinguishable ones. So we might be talking about an electron and a proton here, or maybe in this case, I want to think of the two particles as non-interacting. So maybe I shouldn't think of them as an electron and a proton, but rather somehow we're able to distinguish two different electrons, or maybe I've got an electron and a muon both orbiting around a helium nucleus, something like that, right? They're clearly identifiable particles. Electrons and muons have much different masses. And the question is, what are the states of definite energy? Well, I didn't show it here, but it's actually not hard to show at all. What are the time-independent Schrodinger equation solutions? Through further separation of variables, you can show that as long as they're non-interacting, the states of definite energy are just products of the individual states, which we already know about from before. We can just say particle 1, if we're talking about a helium atom, one electron is just in one of its normal definite energy states, and the other electron is in one of its normal definite energy states, except here we're imagining we somehow can keep track of which electron is which. They're distinguishable, okay? So what I'm saying here is that a state of definite energy as a function of R1 and R2 is just a product of the definite energy state for particle 1 times the state of definite energy for particle 2, as those functions of R1 and R2. And in this case, the corresponding energy is just the sum of the individual energies corresponding to these two states. That comes from a further separation of variables, which doesn't take much work at all. The reason I had to, you might say, well, why is there a 1 here and a 2 here? Wouldn't it be enough to just put a psi m and a psi n? Well, not necessarily, because these are distinguishable particles. They may have different masses. They may have different charges. And therefore, these states of definite energy corresponding to particle 1 and particle 2 may be totally different. And the energies may depend on the mass and the charge of particle 1, the mass and the charge of particle 2. So we do have to keep them straight like that. So states of definite energy for a pair of particles is just products of states of definite energy for the single particles. We already know how to find that kind of stuff. So we'll leverage that quite a bit, okay? And again, these are the corresponding symbols for the single particle states. And I'm sort of breaking with what you saw in Griffiths here, in that I don't know that he necessarily uses this kind of notation. What about if we have indistinguishable but still non-interacting bosons? Okay, that's not the case of electrons, but we have to imagine some other like helium atom with two bosons orbiting around the nucleus. I don't know how you would set that up experimentally. Well, in that case, all we need to do is symmetrize this state to get a state of definite energy. So the states of definite energy that are allowable states for bosons have to be symmetrized, and they're the closest thing you can get to a pure product state. What you do is just say, well, particle 1 is in the state of energy Em, and particle 2 is in the state of definite energy En. But we don't know which one's particle 1 and particle 2, so we better switch the two variables and add them together. That's the symmetrized state. So again, the energy is just the sum of the two. Here, I don't need to specify, psi m and psi n. Those are the same kinds of functions here, because we're talking about indistinguishable particles. So they have the same mass, same charge, same everything. And so they have the same set of eigenfunctions in that case. And similarly for fermions, we just anti-symmetrize. So it's like a product state. Well, not quite a product state. A anti-symmetrized product state are going to be the states of definite energy in that case. Okay, now notice that there can be quite a bit of degeneracy in this case. If we imagine, let's just take, for example, the hydrogen atom case. So we imagine I've got two distinguishable kind of particles in a hydrogen atom, right? Both of them are playing the same role as the electron. The protons are, maybe it's a helium atom, two identical particles, and the non-identical particles, so we can identify them, and we just have to add the energies together. I might say, well, particle 1 could be in the first excited state and particle 2 in the ground state, or particle 1 could be in the ground state and particle 2 in the first excited state. They would both have the same energy, because in both cases we're adding together, in both cases we're adding together the same two energies. So we should expect a lot of degeneracy in this case. So let's do a practice problem with that. This is on a different worksheet. We'll get back to the last problem on that worksheet. I've been sort of madly adding different content to this because I realized the discussion I had in the slides and the discussion in Griffiths seemed to me not quite enough to digest all the stuff that was going on. So we're going to do problem 1 in the worksheet that's posted under today's date. And here we're imagining, again, we're just limiting ourselves to one dimension. So particles living on the x-axis only, just like back in chapter 2, except there's 2 of them. And we're imagining both of them are subject to a one-dimensional harmonic oscillator potential, the usual mass m and resonant frequency omega. And in A, B, and C, we're going to consider the case of distinguishable particles. They have the same mass still, so and they're in the same potential energy function, but somehow they're distinguishable. B is the case where they're identical bosons, and C is the case where they're identical fermions. You know what the individual particle eigenfunctions look like, and you know the corresponding energies, n plus 1/2 h bar omega. So what I want you to do is find the states and corresponding energies for the lowest energy eigenvalue, first excited and second excited states, and also specify what their degeneracy is. How many states, different states are there corresponding to the lowest energy eigenvalue, next highest, and next highest after that? And you'll find the degeneracies are often not, when we say degeneracy equals 1, that means there's only one state. Degeneracy of 2 means there are 2 different states with the same energy. So that's how you specify the value of the degeneracy. So if you're on Zoom, go look up that worksheet under today's date. And we're doing problem 1, which is on the front. I think, why don't we do A together, and then I'll set you going on B and C. And before I take this slide off, I just want to point out in A, we're talking about distinguishable particles, non-identical particles. And we see in that case, the states of definite energy are just products of the individual wave functions that corresponded to individual single particle states of definite energy for the harmonic oscillator. And the energies of those states are just the sum of the two energies. Okay, so sorry, I'm looking at A here. The kinds of states that are of definite energy look like psi n. Remember, for the harmonic oscillator, n could be 0, 1, 2, 3, 4, right? Of x1 times psi m of x2. They could be any product state like that. And the corresponding energy is just the sum of the two energies of those individual states, right? So here we have n plus 1/2 h bar omega plus m plus 1/2 h bar omega, which is, if I add these things together, I get n plus m plus 1 h bar omega. Okay, and now what I've got to do is try to write down the one that's going to have the lowest energy. Of course, I want n equals 0 and m equals 0, right? So in this case, the lowest state is going to be psi 0 of x1, psi 0 of x2. There's only one way to write that state, right? I can't, there's going to be only one state that has the ground energy. I've got to choose n equals 0 and m equals 0. The energy itself will be n and m are 0. So the energy is going to be just h bar omega. And there's only one of those states. So the degeneracy is 1. How about the next highest state? Well, the next highest one of these has got to be 1. And it matters in this case because they're distinguishable, whether particle 1 is in the first excited state and particle 2 is in the ground state, or vice versa. So I have two states that have the next highest energy, which is psi 0 of x1, psi 1 of x2, and a totally separate state, psi, maybe I'll write it as psi 1 of x1, psi 0 of x2. Both of those have the same energy. Notice it's 1 plus 0, so this is going to be 2 h bar omega. And the degeneracy is 2 in that case because there are two different ways to do it. You help me figure out the next one up because we're supposed to do the lowest 3 energies. What states are going to have the next highest energy up? Okay, psi 0 of x1, psi 2 of x2. Certainly, there's also going to be a psi 2 of x1, psi 0 of x2. Is that it? There's one more, 1, 1. That's just because of the nice simplicity of the energy form here. Psi 1 of x1, psi 1 of x2. Okay, and you put in a 1 and 1, I get 3 h bar omega. There is the energy for all 3 of those states, and there are 3 states. So the degeneracy is 3 there. Okay, now these are for what you're going to do in B and C is you have to appropriately symmetrize and anti-symmetrize these for bosons and fermions. That's going to change what possibly the values of energy that are allowed and certainly the degeneracy of those states. So try to fill in parts B and C corresponding to identical bosons and identical fermion states. You good? Okay, should we discuss B together? B is we want to discuss how does the fact that these are no longer distinguishable, but rather identical bosons affect what states we have and how many of them. We'll find out the energies are kind of the same. So if we're talking about identical bosons, the first thing to realize is they've got to be appropriately symmetrized. And so this is the generic form of a symmetrized version of a wave function. Is there any way to choose m and n both equal to 0 so that we would get that same lowest energy h bar omega? Yeah, sure. And in fact, the form that we gave before is already symmetric under exchange of 1 and 2. If you symmetrize it and then renormalize it, you'll get this function back again. So symmetrizing doesn't do anything to this function. It's already symmetric under exchange of the 1 and 2 variables. And again, I'm using, I can't remember if Griffiths does that, you can tell me, but just out of laziness, because it's a pain to write x sub 1 and x sub 2, I'm just writing 1s and 2s there, but you're supposed to be thinking x1 and x2. They're variables. It's just kind of a pain to write all these things over and over again. So there is a state of this lowest energy where n and m are both 0, and it looks the same as the one before. And there's only one of them. The next highest possibility would be where an m and n were 0 and 1. So we certainly have a psi 0 of x1, psi 1 of x2, plus, we got to symmetrize it, psi 1 of 1, psi 0 of 2. That would have, that's appropriately symmetric, and it has energy corresponding to n equals 0 and m equals 1. And therefore, energy 2 h bar omega. What's the degeneracy of that state? Well, there's only one. There's only one way to make it. So the degeneracy is 1 in that case. It sort of combines what was 2 separate possibilities that we had for non-identical particles. How about the 3 h bar omega? Somebody help me write down what could be the possibilities here. Psi 0, 1, psi 2 of 2, appropriately symmetrized, right? Psi 2, 1, psi 0, 2. That certainly is going to have an energy of 3 h bar omega, which is the next highest one that's possible for these product kind of states. And this one's also possible, right? It's already symmetrized, right? It's symmetric under exchange of the 1 and 2 variables. So that's a separate state. Psi 1, 1, psi 1, 2. Both of those states have energy 3 h bar omega, and therefore we get a degeneracy of 2. Questions on B? All right, let's try and see if we can quickly go through and work out C. The only difference here with C is that we've got to anti-symmetrize. How about how many states do we have of energy h bar omega? 0, because when I anti-symmetrize this state, I get 0. That's not a normalizable wave function, so I can't renormalize it to be normalized. I get the 0 wave function is not an allowable eigenfunction. So this one's not allowed. In other words, there are no states, so that's not the lowest energy state anymore. We could sort of just leave this row out. For identical fermions, that's not an allowed energy. In this case, the 2 h bar omega I could get by anti-symmetrizing like this. Any other possibilities for 2 h bar omega? I don't think so. And so we have one of those, that would be the lowest energy or the ground state for the system of 2 non-interacting fermions in harmonic oscillator potential. And then for the first excited state, we would get this anti-symmetrized version of this. And what about this one? Can't happen, right? Because when we anti-symmetrize that one, it goes to 0. And therefore, that would be the first excited state. It has energy 3h bar omega, and there's a degeneracy of 1. We're supposed to get the 3 lowest energies, so I got to go 1 higher now, right? What are the possibilities for 4h bar omega? Yeah, well, we certainly have 0, 3 kind of possibility, right? And it's got to be appropriately anti-symmetrized. Whoops, this is supposed to be a 2. Psi 0 of 2. Anything else? 1 and 2. Yeah, anything that adds up to 3 here is going to give the same energy, right? So I have 1 and 2 also. Psi 1 of 1, psi 2 of 2, minus psi 2 of 1, psi 1 of 2. And I think that's the only possibilities. So the degeneracy of that 4h bar omega energy state is 2. Okay, so imagine this. If this were on the final exam, oh, you've got the energies for the infinite square well, and like figure out what the degeneracies are there. It's going to be a little bit different than the harmonic oscillator, because here it has a nice simple one that has an n squared in it, so that's going to mess with the degeneracies a little bit more, make it harder to be degenerate. So I don't think I gave a problem like this in the homework, but it's something that is worth trying to do in another context just to be familiar with it. Okay. Let's just finish by talking about a little bit of language here, right? We earlier on, there we go. Earlier on, we said, when does it make sense to say I've got a wave function that corresponds to particle 1 being in a particular state and particle 2 being in a particular state? And we decided that that only made sense to speak like that when we had a product state like this. Now, we've just found out that we can't have pure product states like that for identical bosons and fermions. We've got to symmetrize or anti-symmetrize. By definition, it's not a simple product anymore. And so the question is, well, how are we going to speak about it in that state? Because it seems like with the Pauli exclusion principle, people do say things like, well, in a helium atom, I've got a helium atom, one of them is in the ground state orbital, and the next one's, in an upper orbital or something like that. We're speaking as if the 2 electrons have particular states. So there's got to be something that works for identical fermions. Okay, so again, if we have distinguishable particles, and they're in a pure product state like this, we would say, oh yeah, for sure, particle 1 is in this state and particle 2 is in this state. That makes sense to use that language here. What about if we have indistinguishable bosons, which has a symmetrized state like this, or fermion? We still will, when it's in these symmetrized state, use the kind of language that if I've got a combination of psi m and psi n, here I'm writing it as if they're definite energy individual particle eigenstates, but they don't necessarily have to be that way. But if I've got this appropriately symmetrized version here, or the anti-symmetrized version for the case of fermions, we will say one particle is in the state psi m, the other particle is in the state psi n. I'm not going to say which one's in which, but I'm going to say one is in one state and one's in the other state. Just like when we have 2 electrons, you don't say which electrons in the ground state and which electrons in the second excited state. There's no sense to that if they're identical. Okay, so let's just make the statement of the Pauli exclusion principle. It says that no 2 identical fermions can exist simultaneously in the same quantum state. Same quantum state here means exactly the same state. Now we have to be a little bit careful, because if they're fermions, they can't be in a pure product state. They've got to be in an anti-symmetrized state. And so when we say, we don't want to say particle, electron 1 is in a certain state and electron 2 is in the same state, because it's got to be anti-symmetrized. And certainly those states don't have to be energy eigenstates. Often when we think about the Pauli exclusion principle, we're thinking of individual particle energy eigenstates in the case where they're non-interacting, like individual kind of hydrogen atom wave function states, but they don't have to be that case. So when we're saying it makes sense to talk about the states of the two particles, if they were distinguishable, we might talk about it like this, but if they're identical fermions, we're really referring to an appropriately anti-symmetrized state. And what the Pauli exclusion principle is saying, it's impossible, or they cannot exist, where those two states that are appearing here in the individual products of the anti-symmetrized versions are the same state. And well, we have enough time to do this. Let's just say it in words. How would I prove if I say the Pauli principle is saying they can't be in the same quantum state? The same quantum state means exactly the same state. How would you justify that we could say that identical fermions can't be in the same state? In other words, whoops, I'm not sure what happened there. Somehow. Whoa. Not sure what's going on here, but whoa, something's gotten really messed up with this. Is that okay? Well, I'm going to have to sit at the computer and do this. What I'm saying is they have to be in this kind of state. What's the problem with psi A of x being exactly equal to psi B of x for identical fermions? Yeah, it's anti-symmetric. So when I form that combination in blue, I'm going to get 0. Now, normally, if we get something non-zero, we just renormalize it so it's a normalized version after we anti-symmetrize. But here, when we anti-symmetrize, we get 0, and there's no way to normalize it, and that's not an allowable state if you have the 0 function as a function of x1 and x2 or r1 and r2. So the proof is really simple. If they're in exactly the same state, this combination is 0, and that's the required combination for identical fermions, and therefore they can't be in the same state. Now we're going to have to tease out some of the details or intuition about this a little bit, and we'll do that. I still haven't decided if we're going to do like a practice worksheet tomorrow and just continue this kind of stuff on Friday. Maybe I have to think about it a little bit, but we'll keep talking about the Pauli exclusion principle, because in some ways, if you think about it a little bit, it seems very confusing, or, because I could make psi A and psi B just a tiny bit different. Maybe they're almost the same Gaussian, but they just slightly don't overlap. Is Pauli really saying that's okay? No problem with that. We'll think about that.